Looks like I've got homework 3A here. Today we're going to be talking about hydrostatics, and the example I'm going to be working for you in class today I think will help you to finish up the calculations that are due by 5 o'clock on hydrostatic force. If you'd like to also include a brief write-up that describes the purpose of the experiment and the objective and what you saw, I think that's a great addition. It'll probably help you to learn more, but strictly speaking, all I'm going to require for this one is just the calculations. During lab today, we're going to be working with a program called Water Gems, and I emailed you some information yesterday on how to get to the Bentley website. I think a couple of people have told me recently they had trouble downloading the files, but and a few other people have said that they got it to work. So that may be browser differences or maybe some website issues that Bentley is having. If you don't have Bentley Water Gems installed on your computer, that's okay. We'll just use the tablet computers that are back in the cart there, the laptop cart. So you don't need to have the necessarily have that installed on your computer. It's available on lab machines as well. Homework 3B is going to be due on Tuesday the 24th of September. So that's a week from today, your next set of assignments there. So any questions on the announcements? Kind of a lot going on. All right. Well, we're going to talk about hydrostatic forces on flat surfaces today, and one of the important things that we have to do when calculating the location of hydrostatic forces is consider the area moment of inertia of a shape. And at the back of your book are a couple of formulas for area moment of inertia, if you don't remember them from statics when you had this sorts of things. But almost exclusively what we'll be calculating is the area moment of inertia around the x-axis. Most commonly it'll be for a rectangle. And so, for example, a submerged rectangle, we'll consider the location of the force relative to the centroid, and the formula that we're going to use requires the formula for I, which is the area moment of inertia. And so AB cubed divided by 12, where A is the width of the rectangle, B is the height of the rectangle, we cube it, divide by 12. The back of your book has other shapes as well. The other one that we'll occasionally use is the circle. I don't think any of the rest of these will come up, but well, maybe the ellipse will actually. I think one of the examples that we work in class is for an ellipse. But I wanted to let you know when we calculate I, where that comes from and what it's based on. The types of problems that we're going to solve are problems like this, where water is pressing up against a gate, and in this illustration you can see that there's a hinge on a gate, and so that the water pressure that's pushing to the right on the gate would be forcing the gate open. It would be causing the gate to be open and the water would be pouring out over that ledge. So the types of problems we'll solve is a question like how hard is the water pushing on the gate there? And so for a problem like this, if we were going to break it down into a shape, then what you'd need to keep in mind is that the shape that's relevant to the hydrostatics of the situation is only the shape that's underneath the water line. The fact that there is some, the plate continues above the water line is irrelevant to us. All that we'd need to be concerned with would be the submerged height of the shape. And remember, B is the parameter that we give to the vertical height of the plate, and it has some width A. Now, some important terms that we use for calculating the magnitude of the force is delta H. And let me raise the screen so I can show you what dimension delta H is and some of the other things that we're going to be measuring. If we have a plate, that's in an unfortunate spot right there. Let me move it out of the way a little bit so that it's not right on the seam. Is it off the seam now? We'll do that. All right. So if there's water up to the very edge of the tank, so it's completely full, then the centroid for this shape, this is a just a rectangular plate, the centroid is in the center. And so vertically speaking, the centroid would be here, and delta H is the vertical distance up to the surface. So delta H goes up to the surface of the tank, and it's the vertical distance. And the reason why it's important is that when we calculate the magnitude of the force, it's related to delta H. That's how we're going to calculate the magnitude of a hydrostatic force. Now, in this case, you can see that the plate is at an angle. Y bar, the inclined distance from the water surface to the centroid, is going to be the distance that goes along that inclined angle up to the water surface. And so this is Y bar. And if the plate was vertically oriented, then delta H and Y bar would be the same. But in this case, since they're at an angle, they're not the same. Y bar is greater than delta H. Now, any questions about that so far? If we know delta H, we can calculate the pressure at the centroid. Let me drop this down again. The centroid was here in the center, and if delta H is up to the water surface, does anybody remember what is the formula for calculating the pressure at some depth in terms of delta H? Gamma times delta H. Exactly right. So the pressure at the center, the water pressure at the center of the pipe is P bar. Pressure at the centroid. And the YCP is it's the inclined distance from the water surface to the center of pressure. Now, the hydrostatic force that we're talking about is, let me just erase this again. I guess I put it up prematurely. There's an equivalent hydrostatic force that is that's a result of all the little pressures that are acting on this. If you think about it, there's a water pressure all the way up the surface, and it's decreasing as we go higher up. You know, the pressure at the bottom of the plate is greater than the pressure at the top of the plate because the bottom of the plate is lower than the top of the plate. But we could integrate that pressure. So force is pressure times area. If we take into account all of that pressure acting over the entire area, and we instead want to represent it as a single equivalent force, so there's one big force acting on there, then we'll call that the hydrostatic force. And the hydrostatic force is equal to the pressure at the centroid multiplied by the area. And so the force, when I put a bar over the P, that means the pressure at the centroid. You'll see that in the text, that sometimes they say P bar, and that means the pressure at the centroid. So the magnitude of the force is the pressure at the centroid times the area. But the force doesn't itself act at the location of the centroid. It's a little bit further down than the centroid. And so calculating the location of that force is where YCP comes in. And YCP is the distance along the inclined length from where the force is located up to the water surface. And so there's three main distances. There was delta H, which goes from the vertical, from the water surface to the centroid. There is Y bar, which is inclined from the centroid to the surface, and then YCP is inclined from the surface down to where the hydrostatic force is located. And the hydrostatic force will always be a little bit lower than the centroid. Does that force not act on both sides of it? It does, yeah. But if we had, let's say, there will be some examples will work where it's only acting on one side because maybe the plate is acting over a gate, or it's covering a pipe, something like that. In this case, yeah, there's a hydrostatic force on both sides. If we were just calculating the force on one side of the plate, is what we've been taking a look at till now. If the object in question is oriented at some angle alpha, what this diagram shows is that the relationship between y bar and delta h is that delta h, remember, is the vertical distance from the centroid to the water surface. That's y bar times the sine of alpha. And this diagram, I almost hesitate to show it to you because it seems so complicated. It takes a while. You have to stare at it for a while to finally make sense of what this diagram is getting at. So it may be more confusing than it is helpful, but if you have some irregularly shaped area and it's in the water, when you look at it from the side, it's oriented according to the angle that's described by alpha. And if you look at it straight on, so see that where it says C, C, so if you had view CC, so you were looking at it from this direction, then that's what it would look like. And what this is illustrating is that y bar is the distance from the surface to the center of area. Centroid is the center of area. A little bit lower than the centroid is the location of the center of pressure. And you can find the inclined distance from the surface to the center of pressure by using the formula for YCP. And I haven't shown you the formula for YCP yet. We've talked about how you can find y bar. We've talked about how you can find delta H. But YCP, it's not that bad. Here's the formula for it. It takes into account y bar, which remember is the inclined distance from the centroid to the surface. Now I is the area moment of inertia that we started the lecture talking about, area moments of inertia for different shapes. And it's I divided by y bar A. Okay, so we're going to put that into practice by taking a look at several examples today. The first of them is what if we had some sort of a shape that looked like this, hypothetically speaking, right? So what if you had something like this, that you had a measured distance of 125 millimeters. Then what would be the delta H, what would be the y bar, the YCP, the moment distance, and so on. So let's take a look at this case. If it measured depth is 125 millimeters, we've got that bar that the annulus is installed on. And 125 millimeters, what that means in this case is that the water surface is going to be above the top edge of that. And so we'd have, it's a given that it's 0.20 meters down to the bottom edge up to that top edge. And it's, tipping about some pivot point there. And we know that this face here is 0.10. That's the distance along that entire face. And so what that means is that the center of it must be 0.05 meters. And so above, if the measured depth is 125 millimeters, then that means it's going to be 0.025 meters from this edge to the water surface, and then 0.075 meters from there up to the total edge. And so that would be, we know it's 0.2 overall. 0.1 is here, then there's another 0.025 meters, and then 0.075 meters, and altogether that works out to 200 millimeters, which is the distance from the edge up to the top of the annulus. Okay, so what is the delta H here? So delta H is depth to centroid. Okay, here's the centroid for a rectangle. Vertically speaking, it's just in the middle of it. And so the depth of the centroid will be the depth from the water surface to the edge of 0.025 meters, and then the 0.05 meters from the edge to the center of area. So in this case, the delta H would be 0.075 meters. And since it's vertically oriented, since it's not at a tilt, y bar is equal to delta H. Anytime the object is straight up and down, we can say that those two are equal. So it's 0.075 meters is the y bar. Now YCP, we're going to have to take into account what is the area moment of inertia. And in this case, the width of the object, 0.075 meters. The height of it, B, is 0.10 meters. Those are givens for that front face of the object. And so the area moment of inertia about the x-axis is AB cubed divided by 12. And so it is 0.075 meters, 0.10 meters cubed divided by 12. So the area moment of inertia is 6.25 times 10 to the minus 6 meters to the fourth. The units here are meters to the fourth. So the formula for YCP is y bar plus I over y bar A. 0.075 meters plus 6.25 times 10 to the negative sixth meters to the fourth divided by 0.075 meters, and now multiplied by the area. So what we're trying to find is, with the YCP, is where is the force acting? YCP is going to tell us, you know, there's the water pressure acting on that face. There's some equivalent hydrostatic force. The water is pushing on that face, and we want to know how deep underneath the water is that force located. That's what YCP will tell us. And when we go through and do the calculations, we get the YCP is 0.0861 meters. That's the location of the theoretical hydrostatic force. Any questions so far? Any at all?
Are we not using alpha because the weight keeps alpha at 0?
So you're talking about the alpha that was in the previous slide?
Yeah.
It's because it's straight up and down.
Okay.
Yeah. It's because of the angle of that face being vertically oriented that we don't have to use alpha to calculate y bar. Other questions? We haven't yet calculated the magnitude of the force, but we've just found out where the equivalent hydrostatic force is going to be located. And so what that means is that the force is going to be 0.0861 meters beneath the water surface is where it's going to be acting. This is the hydrostatic force. And of course, if the measured depth is 125 millimeters, that means from the top of the device down to the water surface is 0.075 meters. Okay. So what is the magnitude of the force? It's going to be the pressure at the centroid times the area. In other words, it'll be delta H times gamma times the area. Okay, delta H is, as we found before, 0.075 meters. The gamma is 9810 newtons per meter cubed. And the area is 0.10 meters times 0.075 meters. So the magnitude of the hydrostatic force, theoretically, 5.5181 newtons. And that's the theoretical hydrostatic force. Why is that theoretical? Because we've just used this equation, P bar times A. This is the hydrostatic force equation. We have another thing that we measured. Remember, by how many weights we put on to get it balanced? With adding those weights, we also have a measured hydrostatic force that we can come up with. But based on the theory of hydrostatics, those are the equations that tell us the location and the magnitude of the hydrostatic force. Okay. Well, let's consider the issue of what is the, if we had a certain weight that had been measured. What if we had measured for mass of 325 grams? How does that give us an actual force? This is the theoretical force on this side. For mass 325 grams, what's the actual force? Okay, so first of all, that's 0.325 kilograms times the acceleration of gravity. That works out to 3.1883 newtons. So that is the force that is coming down here at W. That's the weight that had been applied. Now what's the moment distance? We already know that the moment distance to get this thing to tilt counterclockwise is 0.275 meters. And how does that compare to the moment distance that was over here? Like, what we need to know is the ratio of the moment distances. So the counterclockwise moment distance is 0.275 meters. That's the moment distance from the edge to where the weight is applied. What's the moment distance from the edge to where the hydrostatic force is? So what's the clockwise moment distance? Based on what I've given you so far, how can we find the clockwise moment distance? Perfect, yeah. So the clockwise moment distance is the 0.075 plus the YCP. And that total length is 0.1611 meters. Okay, so the weight is further away from that point of rotation than, the hydrostatic force isn't quite as far away. So what that means is that we expect that the actual measured hydrostatic force is going to be some ratio of the moment distances, 0.275 meters divided by 0.1611 meters times 3.1883 newtons, and that gives us an equivalent force of 5.4425 newtons. And that's the actual hydrostatic force. Can someone double check that calculation to make sure it works out? All right. So this is the hydrostatic force, that we had to counteract. We had to counteract this actual hydrostatic force, and so we were measuring it indirectly. We couldn't actually measure the water pushing on this, but what we could measure is how much additional weight we had to add on this end to counteract it. And so if we calculate the difference between the two, the difference is going to be the theoretical minus the actual divided by the actual times 100. And so what we had was 5.5181 newtons is theoretical, 5.4425 newtons actual divided by 5.4425 newtons times 100. Then the percent difference is 1.39%, and that's positive, which means that our theoretical amount was higher than the actual amount. So theory too high. All right. So that's if the water was up above the edge. If the measured distance is greater than the 100 millimeters from the bottom up to the top. If it was less, if it was only partially submerging that face, if we had, here's the bottom and here's the water surface, what if measured depth equals 70 millimeters? Okay, that would mean that we'd have 0.070 meters and then 0.13 meters. And we'd want to do this whole process over again to find where's the location of the force, the magnitude of the force, and so on. So in this case, delta H would simply be 0.070 meters divided by 2, because the centroid would be halfway between where the water starts and the bottom edge of the surface. And so delta H is this distance from the water surface down to the centroid. And so it doesn't matter what's above the water surface. Now the relevant dimensions that we're looking at are 0.070 meters, and then the width of it is 0.075 meters. This is the shape underneath the water line. Okay, so delta H is 0.035 meters. And since it's vertically oriented, y bar and delta H are the same. So that's also equal to y bar. YCP is going to be y bar plus I divided by y bar A. And the formula for I is AB cubed divided by 12, where A is the top dimension, B is the vertical dimension, and so that if we calculate the area moment of inertia, it's 0.075 meters multiplied by 0.07 meters cubed divided by 12 the area moment of inertia about the x-axis is going to be 2.1438 times 10 to the minus 6 meters to the fourth. Okay, so we can substitute those known values here into the formula for YCP. That gives us a y bar of 0.035 plus 2.1438 times 10 to the minus 6th meters to the fourth. And the y bar again, 0.035 meters. And then the area, 0.075 meters times 0.07 meters. And the YCP, if we do those calculations, 0.04667 meters. So what that's talking about is from the water surface down to where the hydrostatic force is actually located. Let me draw that. So it's from the water surface to the location where the hydrostatic force will be. The hydrostatic force is going to be below the centroid, and what we know is that the YCP is 0.04667 meters. So that is how far beneath the water surface that force is located. The magnitude of the force we calculate by P bar A, which is delta H times gamma times the area. Delta H is 0.035 meters. Gamma is 9810 newtons per meter cubed. And the area is 0.075 meters times 0.07 meters. The hypothetical hydrostatic force is 1.8026 newtons. That's just based on the hydrostatic equation, the equation for the location of the centroid, and so on. What if for this, excuse me, what if the measured weight had been 115 grams? Okay? So we measured 115 grams. So that 115 grams is 0.115 kilograms. Multiply that by G, and that gives us 1.12815 newtons. So that is how much weight is on the end here, counterbalancing the hydrostatic force. So if we had that weight at W, then we'd need to look at the ratio of the moment distances again. So the moment distance ratio is going to be 0.275 meters for the moment distance from the edge to where W is located. And the distance from the edge down for what the clockwise force, the hydrostatic force, is going to be the 0.13 meters plus the YCP. And so that distance of 0.13 plus 0.04667, that moment distance is 0.17667 meters. So we multiply the ratio of the moment distances by the force that's located at W, which was 1.12815 newtons. And that would tell us that the actual hydrostatic force was 1.756 newtons. And that's actual hydrostatic force. And again, we're not able to measure that hydrostatic force directly. The way that we can measure what the hydrostatic force is by how much weight we had to add to put the balance back into equilibrium. So we can calculate the percent difference, once again, by just the theoretical value minus the actual value divided by the actual value times 100. Okay, so our theoretical hydrostatic force that we had measured was 1.802 newtons. And the actual force was 1.756 newtons. Divide by 1.756 newtons times 100. In this case, if these had been our measurements, if we had measured a depth of 50 millimeters and a mass of 115 grams, then the percent difference would be 2.7%, meaning that the theoretical force was too high by 2.7%. Well, if you remember that it was denominated in millimeters, right? And so one of the possible sources of error is that the line was between one of the millimeter bars, and you had to say, well, it looks like it goes up. And so if you're measuring 70 millimeters and you're off by 1 millimeter, that's going to be 1% error right there, like if it's just in between the lines. And the other issue is, remember in chemistry when you're doing experiments, the meniscus, where the water level rises up on the edge. And so if someone measured, used the top face of the water meniscus instead of the bottom, that's another source of error. The other thing is if it wasn't in equilibrium, if it wasn't actually level, so maybe you put in too much water or not enough water, and it wasn't in the genuine equilibrium condition that you thought it was. Those are, I think, probably the main sources of error. The hydrostatic equation is a fundamental equation, and so it's not an empirical equation that is going to have error built into it. It's going to be pretty good. And like I mentioned before, when I've run this experiment back in the lab, I get the theoretical and actual values to agree about 1%, within about 1%. Yeah. All right. So there I've given you the two examples. Those aren't probably the same numbers that you took back in the lab. You had different measured depth and a different mass, but I hope that going through that process will aid you in finishing the calculations by 5 o'clock. If I happen to be out of my office when you're done, you can just slide it under my office door. But otherwise, I should be in during the afternoon after our lab concludes. Well, now that we've done that really specific example, let's work some of these more general examples that are in the slides. So, revisiting the idea of a gate where water's pushing against the gate, what's the magnitude and the location of the hydrostatic force? Now, we're not talking about F, the force required to hold it closed. We're talking about the hydrostatic force at first. What is the magnitude and the location of F? So the steps, I'd like you to attempt this on your own. The steps that you're going to need to go through to calculate the magnitude and the location of F is, first of all, remember that we identify a few of the dimensions. So you find out what is delta H, what is Y bar, what is YCP, then calculate the pressure at the centroid, then calculate the hydrostatic force. And once you go through that process, then you'll know the location of the force and its magnitude. All right, so I'm going to give you a couple of minutes. Consult with the people sitting near you if you get stuck and don't know. But delta H is the distance to the centroid. In words, we call that the distance, the vertical distance from water surface to centroid. Y bar we call the inclined distance from centroid to water surface. YCP is the inclined distance from the center of pressure in other words, the center of pressure is where the hydrostatic force is located. Inclined distance from the center pressure to surface. P bar is the pressure at the centroid. And F is the hydrostatic force. All right, so I'm going to be quiet now. You calculate and find each of those. All right, for this example, A is 3 meters, B is 4 meters. And at 20 degrees Celsius, if we look up the unit weight of water at 20 degrees Celsius, it's 9790 newtons per meter cubed. So we've got a slightly different gamma than we usually use. Delta H is 2 meters. Y bar is also 2 meters since it's an inclined plate. And the YCP, we're going to have to calculate the area moment of inertia, and AB cubed divided by 12. 3 meters by 4 meters cubed divided by 12 gives an area moment of inertia of 16 meters to the fourth. And we can find the YCP using the equation y bar plus I divided by y bar A. Okay, y bar is 2 meters plus 16 meters to the fourth divided by 2 meters, and the area of B times A, that's 12 meters squared. So that is 2.667 meters. The pressure at the centroid, that is the delta H times gamma. So 9790 newtons per meter cubed times the 2 meter depth, and the pressure at the centroid is 19,580 newtons per meter squared. The hydrostatic force will be P bar times A. So it is the 19,580 newtons per meter squared times the area, which is 12 meters squared. So 234,960 newtons. So the magnitude of the force is simply the pressure at the centroid multiplied by the area of the plate. So this is the magnitude of the force, magnitude of the hydrostatic force. The location of the hydrostatic force is, you go down from the water surface 2.667 meters, and that's where the equivalent hydrostatic force is located. And one thing to try and visualize is what's the pressure distribution along that plate. Now, if here's a plate, the pressure starts at 0 at the top of the plate, and the pressure is increasing at a rate equal to the unit weight of the fluid. So this is water, and the pressure is going up as we go down through the fluid. And if the plate is 4 meters, one thing that's interesting is that the location of the force is 2/3 of the way down. What's 4 times 2/3? 2.667, right? And that's what we got when we did this formula, 2.667. Now, don't let that shortcut throw you off. You can find the location of the equivalent hydrostatic force. You know, this pressure distribution acting over the area of the plate has an equivalent hydrostatic force, and it's 2/3 of the way down through the plate, but that only works if the water surface is all the way to the top of the plate. Like in the case of this, where the water surface is below, the water surface is beyond the top of that, then it's not just oh geez, look what I just did. I'm going to have to clean that later. It's not 2/3 of the way down if it's more than fully submerged. If the water level is right up against that edge, then it's 2/3 of the way down. And in this example, this YCP distance, that is 2/3 of from here to here. It's 2/3 of the water depth. If it's 70 millimeters, 2/3 of 70 is 46. So it's only when you're going from the top of the water surface down, and it's not more than I'm not following what you're saying.
Okay, so like you've got what do you call it? Distance between the force and the top of the object right there. Okay, and then from that distance of your right finger to the top of the water, if you were to draw a straight line and then put this force triangle on there, and did 2/3 of that, would that?
I don't think so. No, because the further down you go, the closer the location gets to the centroid. If you're very, very deep, then finally the location of that hydrostatic force is at the centroid. And the reason why is that this is if it's the edge of the plate and it starts from 0 down to some depth. In the case of like it's already partly submerged, like here's the water and here's the plate, then the hydrostatic force distribution is going to be a little bit, a little more, a little more. Okay, so it's increasing, and if you go really, really deep, then the top edge and the bottom edge aren't going to be very different. Like, you know, the center of area for a triangle is 2/3 of the way down, but it's not going to be 2/3 of the way down for a shape like this. So anyways, what you can remember is that the formula for YCP always works. This, as long as you calculate the correct area moment of inertia I, that formula for YCP will always be valid. All right, so here's another example. In this case, we have a plate that's at a 45-degree angle, and we want to find the hydrostatic force that's acting on the top part of that plate. And the steps that we need to go through is to find the depth of the centroid, the magnitude of the force, area moment of inertia, and then the location of the force. So this is a plate that's 2 meters wide and 3 meters tall. We can see from this dimension that it's 3 meters tall This is the side view. And from the front view, now remember, it's at an angle, so we couldn't get the height, since it's at an angle, from a front view. Well, what we can tell is we get an accurate width measurement is 2 meters from the front view of it. And we want to know the depth of the centroid, the magnitude of the force, the area moment of inertia, and the location of the force. So I'd like you to go through and calculate those things while I go get a paper towel and see if I can clean off the whiteboard.
5 meters to the top of the...
Yeah, from the edge. So there's a vertical distance of 5 meters from the edge up to the top. Okay? Other questions? Okay, go through those 4 steps and see if you can find the magnitude and location of the hydrostatic force. You're going to have to remind yourself of some trigonometry for some of the problems that you'll work in this textbook chapter. In this case, the depth of the centroid we know is the center of area for a rectangle is, vertically speaking, half of the distance from the top to the bottom. So here's the centroid. So we can just point with our finger and say the centroid is 1.5 meters down the edge of that plate. Now, in this case, since it's not vertically oriented, 1.5 meters down the edge is not the same thing as 1.5 meters straight down through the fluid. So we need to find what is the vertical component of that 1.5 meters down the edge. And so it's 5 meters from the water surface to the top corner, and then some additional distance down to the edge. And so we can find that it's the 3 meters is the total distance from the top to the bottom, and sine of 45 will give us the vertical component of that 3 meters, and then we only need to go half of the distance. So it's 1.5 meters times sine of 45 will tell us that additional depth beyond the 5 meters from the water surface to the edge that we need to add in order to find delta H. So delta H is 6.061 meters. Yeah?
Could you possibly go the other way and solve y bar first and then solve delta H?
Solve y bar first. Yeah, sure.
So like,
Sure.
it'd be 5 meters times square root of 2 and then add the 1.5 and that would give you delta y.
Yeah, you could find the y bar first, yeah. Once we know delta H, we can find the magnitude of the hydrostatic force pretty easy, just putting it into the hydrostatic equation. The area moment of inertia is going to come into our formula for the location of the force, but we've got a little bit more geometry to deal with. We have to find the y bar, which is the inclined distance from the water surface to the centroid, so that we can put that into the formula for YCP. All right, so are there any questions on this example for an inclined plate? What's the difference between y bar and delta H?
No, in the calculation, to find delta H, you use a y bar, don't you?
He's talking about y bar sine of alpha.
No, what I did here was because I was given the dimension of 5 meters from the surface to the edge, I didn't. You're thinking about the previous slide here? Yeah, so if we knew delta y, so now that we've calculated, it's 8.572 times the sine of alpha. The sine of alpha will be 0.707. So if we have 8.572 and multiply it by 0.707, it should give us that delta H that we'd already found of 6.061. Other questions? All right, here's another example. This time it's an elliptical gate. And one thing to point out is that in the formula for an ellipse, the area moment of inertia formula is pi AB cubed divided by 4, not divided by 12. And then the other thing is that the dimensions A and B, rather than being the entire width of it and the entire height, A is just from the centroid to the edge, so A is only half of the width, and B is only half of the height. So that's a little trick, I guess, a tripping point, a tripping hazard that you need to be mindful of as you solve problems like this. So we've got an elliptical gate covering the end of the pipe, and the geometry here, if you notice, it's a 4-meter diameter pipe, and so the pipe itself is circular. It's just that we've cut the pipe at an angle, and that's what makes the gate that goes on the top of it be elliptical. Think about if you have a circular can, like this can right here, Arizona green tea. If you have this can and you cut it at an angle, then the shape that has been cut is an ellipse, and that's the shape of the gate here. It has a total height from top to bottom of 5 meters, and then the 4-meter diameter that's given here, that tells us what the width of it is going to be. Okay. So in this one, we're going to find the magnitude of the force that's acting on the gate, this gate that's keeping water from going inside of the pipe. We'll find the inclined distance to the center of pressure, so we'll find YCP. And then how much force would be required, how much force at F would be required in order to open up that gate. Now, I owe you guys 2 minutes from a previous lecture, right? Okay. So we're going to get out at 12:13 today. Let's see if we can do this in the next 5 minutes. The magnitude of the force is going to be, the force is delta H gamma times area. So what is delta H? The distance from the top to the centroid. Well, here's the centroid. It's going to be 8 meters from the water surface down to that hinge, and then another 2 vertical meters to the centroid, because you can see that's a 4-meter diameter pipe. So the vertical component of that to the centroid will be 2. So it's going to be delta H is 10 meters. The unit weight here is 9810 newtons per meter cubed. And the area of an ellipse is pi AB. Okay, it's pi, and A is 2 meters, and B is 2.5 meters. So the area of the ellipse is 15.708 meters squared. So we'll put that here into the formula for the hydrostatic force, 15.708 meters squared. Okay, that makes the magnitude of the force equal to 1.541 meganewtons. Capital M means mega. So that's 1.541 times 10 to the 6th newtons. Okay, next, the inclined distance to the center of pressure. So YCP formula that we already know, but think about this is a 3, 4, 5 triangle. So it's a 5, 4, 3 kind of a triangle, and we know that the vertical distance from the water surface to the centroid is 10, and so comparing triangles, a 3, 4, 5 triangle, and we want to find what is the distance from the center of the pipe up to where the water surface would be. Now, if you go at an angle, you're going to see that it takes you out of the tank. And so we'd extend that line inclined up to where the water surface would be. So pretend that the water surface continues. That's the y bar distance that we're going to find. And so y bar is to 5 as 10 is to 4. So y bar is to 5 as 10 is to 4. So we can find the y bar distance is 12.5 meters. That's the inclined distance from the water surface to the centroid. Okay, and we're going to use that y bar when we go into the formula for YCP. The YCP is y bar plus I divided by y bar A. And the area moment of inertia for an ellipse is pi AB cubed divided by 4. So that's pi 2 meters times 2.5 meters cubed divided by 4. The area moment of inertia is 24.544 meters to the fourth. Okay, so sometimes instead of writing YCP is y bar plus I divided by y bar A, sometimes it's useful, and this is an example of when it would be better for us to calculate this. YCP minus y bar is equal to I divided by y bar A. And the reason why that's more useful is that it will tell us how far down from the centroid the force is located. So instead of finding where is the force located relative to some water surface, it's going to tell us where is the force relative to something on the plate itself. So when we get back together on Thursday, we're going to continue this example from this point. We're going to talk about why this form of the YCP equation is most useful. So remember, Group B is going to be coming at what time today? This is the second time we've been split. So Group B comes at 2 o'clock. Group A comes at 3. We're going to be meeting actually in here. We're going to start a lab. I think there's nobody else scheduled here in this classroom during the lab time, so the laptops are in here. It'll just be most convenient for us to do the lab exercise in here. And I'll see you at 2 or 3 o'clock.